to measure integration and analysis class. In our previous video, we are able to check solutions to question 1 to 3 of exercises 1A. So we will continue from solving the solutions, which is very important in order to know the applications of the basic definitions and theorem we explained in the first video. So let's go straight. Question number. So we're able to solve question 1, 2, 3. Importantly, in question 3, we have if f is Riemann integrable, don't forget f is bounded, then we have this theorem, then we can say that this theorem is satisfied. The difference between the upper Riemann integral and the lower Riemann sum, the upper Riemann sum and the lower Riemann sum is less than epsilon. So let's go straight to the first question. Question 4 on the textbook we are using. We have suppose f comma g, we have function f comma g and a comma b to r are Riemann integrable. So we want to prove that the addition of those functions are also Riemann integrable, and a comma b, and then the linearity of a function, also holds. Okay, don't forget to subscribe, like this channel, and share it with fellow PhD students. Drop your comments at the comment section. So let's check the proof of this. We have proof. So first, by definition, f is Riemann integrable if, I use the word if, f is Riemann integrable, which is already given by the hypothesis. Then we have the upper Riemann integral, that to be equals to this, and this is equals to this. And then also we know by problem 3 of which we checked the proof in our previous video. So we also know that this also holds for a partition P. They also holds. So we'll be using this fact. Okay. So then let's take our proof from here. That is just facts. Then let's start the proof properly. Let's see. If f is Riemann integrable, then for each epsilon greater than 0, there exists a partition, let's say P1, such that this holds. Okay. Similarly, for the function of g, there exists a partition P2 such that D also holds 1 partition P2, and then this function G P2 A comma B is less than x over 2. All right, so note the properties of supremum and infimum. By the properties of supremum and then infimum, we have the sup of a function, sup over x, the sup of f over a function x. You see f plus g is less than or equals to the sup f over x plus sup g over x. So we have this fact. Then also the infimum is other way over x is greater than or equals to the infimum f over x plus infimum g, infimum g over x. So with these properties, then we have done with the proof. So this means, so this implies that, with this we get the definitions of upper Riemann sum, and with this we get the definitions of the lower Riemann sum. So that means that the upper Riemann sum of f plus g. So let's define the new partition. Let P be the common refinement of the two partitions. Then we know that by the properties of common refinements, the lower Riemann sum of this P1 will be less than this, and then the upper Riemann sum of this will be less than this, and that we have that. So with this and then with this new definitions, then we have our upper f plus g of P over A comma B using these properties will be less than or equals to the upper Riemann sum of f P A comma B, and then of upper Riemann sum G P A comma B. So likewise the lower Riemann sum of f plus g so we have this to be greater than, using these properties now, the lower Riemann sum of f P A plus B and the lower Riemann sum f, that is G P A plus B. So in order to be careful with what you are doing, so let's flip this integral so that we're able to do something with it, with this. So if we flip this integral, then we should have something like this. LF P A comma B plus the lower Riemann sum GP A comma B should be less than or equals to the lower Riemann sum F plus G B A comma B. So then if we subtract this and this, what we have, okay, that is star. That'll be good. Or let's just add star plus star 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 star. So we have a nice properties. So let's see what we have. We have the upper Riemann sum UF plus G B A comma B plus what we have here plus this and then less than or equals to, we have this and this, the upper Riemann integral. It's kind of long. Okay, let's see. Plus the upper Riemann integral for B. Still have meant 2 times to write. So permit me to write it here. So this is plus the lower Riemann sum of this guy, and then lastly we have everything written now. So then let's simplify carefully. So we have this, we have this here, so we have this, and then we have the I've lost one thing. What's that? See, this mistake here now. This is not. So we are working with this and then with this. So after this, this, then we have this. So for that we have the lower Riemann sum F plus G plus B. Okay. Then we can take this guy down here. We have this. Then after that we have less than or equals to. Now what do we have? We have UFP A comma B. Then we have this minus the lower Riemann sum this. Then we have this U GP A comma B. Then finally we have this. So by definition these two guys less than, so by our definition here we have this, we have this less than x1 over 2, less than over 2, since f and g are Riemann integrable. So that means that we have less than over 2, this is less than x1 over 2, and this also is less than x1 over 2, and that's less than x1. So that implies that UF plus G be A comma B minus this is less than x1. Hence F plus G is Riemann integrable. That is cool. So let's check the second. So now I want to show that the linearity holds. Next, we want to show integral ABF plus G is equals to integral ABF plus integral ABG. So integral ABF plus G, that implies F plus G comma B A comma B. Okay, and that also implies F plus G B A comma B. So Then very careful now, this is by definition, so this is less than UF, yeah, so not UF plus G by what we have already shown by the properties of supremum is less than UF comma B A B, and then those U G B A B. So likewise, you have the lower Riemann sum F plus G B E. So we have already shown this also, that this is greater than the lower Riemann sum and the individual function G B. So if we match these two guys together, then following from here, following from this point, so if we pick it from this point, if you flip this, then you add just as what we did here, then this integration is going to follow, and then we have UF plus G B A comma B minus NF plus G B A comma B. This will also be equals to UF B A comma B minus N of P A comma B, and then this will also equals to U G B A comma B minus careful now U G B comma A plus B. So you can just carefully check this notation. So the conclusion or the key here is that since F and G are Riemann integrable, then combining these properties together and this, then we have our integral AB F plus G to be equals to UF plus G upper Riemann integral to be equals to the upper Riemann integral of F comma P to be equals to upper Riemann integral of G, there will be plus, split this, that will be plus U G comma P. So you can also use, either you choose to use the upper Riemann sum or the lower Riemann sum. So anyone you use, you're still going to get the same result. And this is the definitions for F plus G, AB G. So this easily follows from this, and then with the fact that F and G are Riemann integrable. Okay, so that concludes that question. So let's check one more exercise before we move to the next video. So that will be problem 5. So problem 5, we have suppose F A comma B thanks to R is Riemann integrable. They want to prove that the function minus F is Riemann integrable, and a comma b, and then ab minus f is equals to minus ab f. Alright, so don't forget, if f not if f is Riemann integrable on a comma b, that means that there exists a partition. So for any or for each epsilon greater than 0, there exists a partition P such that this theorem holds. F comma PAB minus the logarithm sum this is less than epsilon. Okay, also we are going to use this fact. So note that the sup, let's say the sup x of minus f is equals to minus the infimum of f x or x. So likewise, the infimum of minus f of x is equals to minus the sup of f. So all these are just by definitions of supremum, by the properties of supremum and then infimum. Alright, so let's go to the proof. So now we have the upper Riemann sum. Let's say proof. Let's start the proof. Now we see that the upper Riemann sum of this guy, that should be equals to, let's see, okay, let's define our partition first. Let P be any partition a comma b, and b equals to a naught equals to, sorry, a equals to x naught, x1 dot xn equals to b. So then the upper Riemann sum of this guy for that partition will be summation j equals to 1 to n s j minus sj minus 1. Then the sup, don't forget the definition, sup f over the interval sj minus 1 sj, and then this, by the properties we defined here, this will be equals to minus summation j equals to 1 n sj minus sj minus 1 infimum f sj minus 1 sj. Then if you are very careful, you know that this is just the definition. This whole part is just the definitions of the lower Riemann sum. Okay. Alright. So likewise, we have for this infimum, for the lower Riemann sum rather, lower Riemann sum similarly, we have summation j equals to 1 n sj minus sj minus 1, the infimum of minus f sj minus 1 sj. This also equals to minus j equals to 1 to n sj minus sj minus 1. Then by the properties you define, this also be sup sj minus 1 sj, and this is equals to minus. So this is also the definitions for the upper Riemann sum. So what next? We're almost done. Then let's subtract these two guys. Let's call this one 1 and then this one 2. So then that's what we have. So 1 plus 2, that is not equals to 3. Let's see what is equals to. So we have the upper gamma sum of this plus, that will not give us a nice one. Let's do a subtraction. 1 minus 2. Then we have this minus the lower gamma sum. Now this subtracts this, and then we go this other side. This subtracts this. We have minus n f p a comma b. Okay, then minus, then this will become plus. And that is nice enough. And then by what we note here, we have this minus this is less than external. Then we can see that this minus this is less than external. So then this implies that the upper gamma sum of the negative function is less than external. And this shows x minus f is integrable. So we know just integrable, Riemann integrable. Okay, so let's check the second proof. So we have integral ab minus f, and this is equals to minus fb equals b is equals to n minus b equals b. Then from this is not nice enough, sorry, we have this is the upper Riemann integral. Okay, then we have this to be equals to what? And this is equals to minus n f of p, and then we have this guy also, so minus u f plus p. Okay, then we can now see that, so from this line we derive this, then from this line so now we have minus integral ab f, so and then this shows that integral ab minus f equals to minus integral ab of f. So the key of this question is to know the properties of this, of supremum and then infimum. Once you note these properties, then you are done with the solution. So we are going to continue the next problem in the next video, which they have like 8 questions. Nice question for us to check under this session. Okay, so thank you for watching. See you in the next video.